next up, Vova is going to tell us about foundational multimodal verifiers.
Hello, everyone. Thanks for coming for this talk. I will tell you about our work in National University of Singapore. We've been working on foundational multimodal verifiers. Some of our verifiers you might have already seen earlier at the conference. We had 2 talks on Daphne workshop about Velvet and Whale, and then later on Monday, George and Qiyuan had an amazing tutorial on Whale. So now I will tell you a little bit more about foundations of those tools. What do we build them on top of? Well, given that you are here on this talk, I assume you are interested in program verifiers, maybe even in automated ones. We all know about Daphne. Paris, of course, is very popular now. Viper with Cobra and Prousty and other things. F-Star, Liquid Haskell, GML, Boogie, Tamarin, Proverif, and so on and so forth. So there are many, many of them. That's not even the half. And even though there are so many of automated program verifiers, usually they share something in common, like pipeline. Well, it's pretty easy. You give them the program and the spec, and then they do some magic and transform it to verification conditions, some formulas, which kind of correspond to the correctness of the program, send them to SMT, and then if you're really lucky, then it will say, yes, everything is great, you can chill now. If you're a little bit less lucky, but that's still a great outcome, it will disprove your spec and give you the counterexample. And it's great because you can use this counterexample to refine your program and your spec. But it's not all milk and honey. And of course, oftentimes, if your specification is too complicated, if your program is too large, they can just time out. And if you have experience with using such things, you probably know that in this case, it's really hard to progress and debug what has actually happened. The verifiers which do not suffer from this problem are interactive ones. Usually we'll build them on top of Rock or Isabel or something else. And I'm talking about VST, Iris, HTT, stuff like this. Well, working with such verifiers is, of course, very intellectually fulfilling, and it helps us publishing POPL papers, which we love. And, but using them in practice might not be exactly the most economically efficient strategy because the cost-benefit curve is not that great, right? You will spend a lot of time setting up definitions, proving auxiliary properties, and you will only get some result which you can show to someone, maybe your investors, towards the end of your verification effort. And so now if you want to boost the benefit on the early stages of the development, you can use bug-finding tools. I'm talking about quick check, like property-based testing, maybe model checking, fuzzing, and maybe something more symbolic, like infra-pulse. So bug-finding tools. And more or less, this is it. This is the state of the art. You can kind of split it in 3 groups. Automated symbolic verifiers, interactive ones, and bug-finding tools. And, well, as the slide suggests, we want to target the middle ground. We want to do so-called multi-modal verification. So that means that we want to combine the capabilities of all different provers inside one tool. And we want to build those tools for each domain-specific problem. OK, what's the recipe? How do we even approach building such multimodal verifiers? Oh, sorry, I forgot to mention that these tools, they should, when you start prototyping a system, you should be able to catch the shallow bugs using proof finding techniques, then go on and try to prove something about your program automatically. And only if this fails, you should be able to smoothly transit to interactive proofs. Okay, now, how do we build such tools? When you design a verification framework, there are certain design aspects which you can implement in different ways. I'm talking about program effects, for example, state, termination, exceptions, and non-determinism. Of course, there are much more, but we will focus on these ones. And combining the different treatments of those effects in different combinations will actually give you tools from all these different groups. Let's look at some simple examples. Daphne verifies programs symbolically, so it's a symbolic state. By default, it checks the termination, so it's total. Then also, it will try to make sure that your program doesn't have any failures or exceptions. And also, whenever you have some non-deterministic choices in Daphne, then it will try to verify your specification for all possible choices, right? Now, if we look at VST, VST is by default is partial. If we look at something like infer, then the idea is there is different. It will actually try to find the non-deterministic choices. It will try to find a trace of your program which leads to something bad, like exceptions. And if we talk about property-based testing, then you will try to do the same thing, but instead of using symbolic methods, you will be doing this by executing programs. So concrete methods, right? And in our work, we present Loom. Loom is a system which helps you building verifiers, combining the capabilities of all these different tools from different groups. How we do that? Well, we make it kind of easy to make these different treatments of effects as parameters. So basically, the tools which we build on top of Loom are multi-modal verifiers. And now you might be asking, how do we combine, for example, interactive proofs and automation? Well, the answer is on this slide already. We built Loom on top of Lean. Because in Lean, you get a very nice way to kind of mix interactive proofs together with such powerful automation like SMT and with proof reconstruction or grind and ASOP. And of course, let's look at this simple example. We will be now building with you a verifier which reasons about money managing programs. It's called Kashmir because, well, it's about cash. And we will go through all these effects one by one and start with state, of course. Again, Kashmir is all about money flows, withdrawing money and depositing money. And we also built on top of Loom. That's why it kind of makes sense to assume for now that the programs that we are going to verify are just stateful programs with state being a balance, which is just an integer. And the very first program that we will verify is a simple withdrawal function. It takes the amount that we want to withdraw, then it gets the current balance and updates it. Well, nothing too complicated, but of course you don't want to show user all those like monads, right? They want to see kind of imperative style code. And luckily, with great support for metaprogramming in Lean, using this small metaprogram, we can glorify our code to make it look now more like imperative program, where basically balance now is just like a global variable which you can modify in your function. So this is a front end of our verifier. And even though with this front end it looks fancy, it is still monadic code, so we can execute it directly in Lean. And with this, you can bridge the gap between all these lightweight bug-finding tools like model checking, fuzzing, or property-based testing, basically just implementing them in Lean directly using the execution, and we did it for our verifiers. Now, if you want to start the verification, of course, the first step would be to add postcondition or precondition, so basically add specification. And Loom gives you tooling to amend your front end with specifications. Well, also it gives you the commands to verify your programs. Let's zoom in on this command a little bit. So what do we need to do to enable this tooling from Loom as designers of the verification framework? Well, we have to do two things. First, we have to fix the assertion language. In this case, just predicates on the balance. And second, we of course have to define the weakest precondition calculus. Nothing too surprising. Of course, we'll have to prove some properties about our weakest precondition calculus. But for now, let's for now forget about it, and I will show those properties a bit later. And once you did all of that, you will get two things. First, you will get the proof correct command, which will, given your program, define, based on your specification, the Lean statement in terms of the Hoare triple, which is just a weakest precondition in disguise. And second, it will give you tactic to basically prove such things. So how this tactic works. Exploiting the properties of your weakest precondition, it will generate you a bunch of formulas as a Lean goals, verification conditions. And then, using the automation of your choice, it will try to dispatch all of them one by one. And now, if automation fails and some goals cannot be dispatched, just like easily with SMT or any other automation you picked, you can go ahead and prove things manually. That's how we kind of bridging the gap between automated verification and interactive one. But that was all pretty easy. that was an easy program. Let's go on and verify more complicated programs with loops and see what we do about termination. This is the program that we will verify now. Instead of having only one amount to withdraw, it has the whole list. And, well, the specification is amended. Now we want to make sure that the new balance plus all the things that we have withdrawn equals to the old balance. And we will implement this program simply by, while we still have something to withdraw, like deducting it from our balance in the loop. Looks not super complicated, but of course it has while loop, and Lean as a total language doesn't accept arbitrary while loops, as long as you work in just state monad. Well, in Lean, there is a nice workaround. If you extend the programs that you consider to basically now state transformer with option in the bottom, then you can have arbitrary while loops. So I won't get into too much details, but the idea there is that the semantics of the divergence is just option.none. And now, if you want to reason about these programs, then we first have to, of course, provide the invariant. And second, you might be asking, oh, is our logic partial total? Do we need to provide decreasing clauses or not? Well, the answer is depends. It depends on this option. Remember, I said that the semantics of divergence is option.none. So depending on how you define the weakest precondition on this option, you will get different logics partial total. If you, for example, define it to be true, then you get partial logic. Otherwise, you will get a total one, so you will need to provide the decreasing clause annotations. And in Loom, we can simply control it by setting the specific option semantics determination to either partial total. Now, side remark. Of course, the partial correctness, the total correctness proof is more involved. You have to now decorate your program with all the decreasing clauses. But of course, it will also give you more guarantees. So we have you can do like very simple meta theory proofs. We give you lemmas on the level of Loom to prove that if you have a total correctness proof for your program, then it will never give you option. It will never give you none. So you can always extract the value. Well, now let's add even more stuff to the programs that we consider. For example, if we try to withdraw something that is larger than our current balance, let's throw an exception. Makes sense, right? To do this, we will have to amend the class of programs that we are looking at and add the exception transformer on top. And also now, just for the fun of it, instead of passing the amounts as the argument, let's model kind of input-output with non-determinism. We will be non-deterministically picking the amounts that doesn't exceed our balance and just withdraw them in the loop in the same way as we did. So to do that, we of course will have to add the non-deterministic monotransformer to our monostack. And if you want to verify this code, you will have to do two things first. You will have to say what is the semantics of your non-deterministic choice, demonic or angelic, and you will have to say what is the semantics of the exceptions. Well, we will start with verifying very conventional property. We will just prove the functional correctness for all possible choices and also make sure that your program never throws an exception. To do that, we will have to, of course, choose the demonic semantics for the non-deterministic choice. In this case, it just means that weakest precondition of the choice is for all quantification. And for the exceptions, we will have to choose the failure semantics. So weakest precondition of throw is just false. Now, if you try to verify it with Loom solve tactic, it will basically verify your program. And on the meta-theory level, that means that you have proven that your program never throws an exception with total correctness. So you just have proven the absence of bugs. Now I will show you how tweaking the semantics of these effects. You can also prove the presence of bugs. So do bug finding. First, let's introduce a bug to our problem. It's easy. Instead of choosing the program amounts non-deterministically, we will choose the arbitrary one. And now, of course, this exception can be thrown. Let's try to prove it. Well, first thing, we will have to change the semantics of non-deterministic choice from demonic to angelic. So weakest precondition of throw is now exists. And we have to change the semantics of exceptions from false to true, because now we want to kind of get them right. And this, together with changing the specification to false, will mean that you can only verify your program now if it throws an exception. So if you run Loom solve tactic now, it will verify the program. On the meta-theory level, it will mean that there exists a trace in your program which leads to an exception. And you have proven the presence of bugs. So this is more or less everything about the tour of Kashmir. And here I would usually just go and list the list of contributions. But, well, given that's a POPL, I feel a slight suspense in the audience. You might be wondering, well, isn't it just the extra monads? Come on, we have bazillion papers on the extra monads. Why do we need one more paper about foundations of the extra monads in POPL'26? Well, Loom is not exactly the extra monads. This is the extra monads plus one more thing, which we call ordered monad transformer algebra. And I will try to explain why is it useful. To do that, let's backtrack a little bit and imagine we want to verify arbitrary program. And we want to do it with the extra monads. So what we will have to kind of instantiate? We'll have to give the weakest precondition calculus. We'll have to prove 3 laws. We have to prove that it respects pure bind and also is monotonic. You will also have to define the friendly, SMT-friendly definition of, give an SMT-friendly definition of hot triples in an ad hoc way. And also, you will have to compute the weakest precondition for basic computations like set and get and state monad or lifted computations. And then you get push-button automation. Now, even in this small example, we had to change the monad stack at least 3 times. Does it mean that we also always have to provide new WP and prove these properties over and over again? And that's exactly what Loom helps you with. In Loom, we not only automate the program verification, which arguably has been done by the extra monads 10 years ago, but we also help you, we simplify the process of construction of automated verifiers. How we do that? Well, we introduce this notion of ordered monad transformer algebra, which is the structure on top of your transformers. And I won't explain you what exactly is that. You can read the paper. But it has one nice property. If your monad is application of a bunch of transformers, for each of which you get this instance of this ordered monad transformer algebra, then you can combine them in various ways. But we will be automatically deriving a weakest precondition with all these nice properties for you. Yep. So, and this is it. This was Loom. Loom is designed to build foundational multi-modal verifiers, which are sound by construction. We do proof automation using the extra monad techniques. We add this ordered monad transformer algebra on top to automate the verifier derivation. And also, we build on top of Loom to enjoy all these nice pieces of ecosystem like lean SMT and lean auto to translate goals to SMT and get the proof reconstruction. We enjoy the plausible, which is the lean way to do property-based testing MATLib to get all the formalized math and so on and so forth. And we built 2 realistic verifiers. One of them is Whale, which is the verifier for distributed protocols. And another one is Velvet, which is the verifier for imperative programs. Well, Daphne-like verifier. And now this is it. Thank you very much. I would be happy to take questions.
Thanks for the talk. In your example of finding bugs, you prove that there exists a bug, but do you get a counterexample that you can use to fix your program?
Oh, you mean the counterexample of the example of an input where we throw the bug?
Right.
OK, we don't have the functionality on the level of these proofs now, but we get it at the current stage. We get it from the property-based testing. So we also have, for example, for Velvet, we have the property-based testing harness, which will kind of give you the inputs for which your program leads to a bug. Yeah.
When I see the word automate, I think it can either mean you have a nice theory that like by construction gives you sound verifiers, or you have a bunch of tactics that do sort of optimistic metaprogramming, and when you're lucky, you get a sound verifier. Which one is this?
So this is a combination of both. We have a nice meta theory, which basically means that you have to define less things and prove a little bit less properties. And you also need to do it for each particular transformer. And also we have all these kind of meta programs that using this meta theory will derive the weakest preconditions that you are interested in. So this is kind of garbage in, garbage out principle. We want to derive weakest preconditions such that if you had first order specifications, then your verification conditions that Loom generates is going to be first order as well. And we achieve this by combination of both, yeah.
Thanks.
Yeah, thanks. Really interesting stuff. So when I saw this this monad transformer ordering, I don't know how you called it. I mean, I probably have to read the paper to understand exactly what it is. But the issue of having to reorder the monad transformers sounds like what effect types usually are meant to solve. So would effect types also solve the issue that this transformer thing, reordering thing solves, or is there something fundamentally different here?
Yeah, I'm not sure what exactly, what is the thing that you...
Effect types.
Effect types. Yeah, I'm not, we should, yes, we should maybe take it offline and compare because I'm not entirely sure.
Okay, thanks.
Yeah.
Thanks for the talk.
Yeah.
I have a question maybe related to the previous one. Right, so you showed that if you have like an arbitrary nesting of monads, you get the weakest pre for free.
Yes.
And then you had the example where it was like state of non-det of option or something. Does Loom also help me figure out which monads I want in there and in what order?
Sorry, can you repeat?
Does it also like help me figure out that I want like non-det and state, or maybe I want state of non-det? Like.
Oh, no, yeah, not really. You have to just set up what effects you need. You kind of construct a monad yourself, and then for this monad you will get weakest preconditions, but that's an interesting direction. Maybe we should look into that. Thanks.
Thanks for the talk. When you switch to a non-terminating programs, you can, so you're going to the option monad, but also you're elaborating to something that is fueled, right? That the BDEF is doing a kind of elaboration of your initial program to something that is not fueled and returns into option? Deeply embedded.
So the way we go is basically we do shallow embeddings, and then depending on what type you want to get in the end, what type of programs they want to get at the end, you will get elaborations to kind of all these different monads. Yeah.
Hi. I should. Are you done or?
Yes, go ahead.
Okay.
Last question. You got 1 minute.
First of all, very slick talk. Great talk.
Thanks.
If you were to use separation logic with Loom, would you have to rewrite anything? Do you think it would just fit in the framework?
That's a great question. We are working on separation logic, and we think you can fit it into the framework. And we have some like prototypes. Maybe we can take it offline and I can show you something.
Thanks.
Yeah.
Okay, let's thank the speaker.